Okay, so I've been thinking a fair amount today about the complex structure of a circle. So I'd like to talk about some of the things I've got some formulas for. It's the things I want to talk about are mostly new to my understanding, but I would be very surprised if no one else has gone along the same lines before. So the circle, basically, for a real number row, can be expressed as an equation x squared plus y squared is rho squared. And how are we to visualise this when x and y are complex numbers? So unlike most of my videos, I'm not going to explain everything here. I just want to go in at a fairly, moderately advanced level and just talk about what I'm thinking. So I assume you already know what complex numbers are and so on. So we can start to get an idea of what the complex structure is of a circle when we ask the question, where does a circle meet a particular line? So we can draw a real line, and we have this circle which has, we can draw the sort of real part of the circle, that's the normal round thing. And then we can solve these two equations, x squared plus y squared is rho squared, and we can pick a specific line. We might as well pick the line x is equal to k for simplicity, and then we can solve these two equations, solving this and this simultaneously for x and y. And here's the solution that we get. For x and y, the coordinates x, y, which are on this circle and on this line at the same time, are k plus or minus the square root of rho squared take away k squared. So there's two places where the line meets the circle in general, and we can write them like this. Now, when k is less than rho, the line meets the circle at two real points, and this kind of equation is more appropriate. When k is bigger than rho, in other words, when the line is more than a radius away from the centre of the circle, this is actually the square root of a negative quantity, so it's an imaginary number. And it makes more sense, in fact, to take the minus 1 outside of the square root sign. So then we have the meeting points of the circle, the x coordinate of them is still real, it's just given by k, this amount out here. And then the other coordinate is the y coordinate, which is plus or minus square root of minus 1 times this quantity here, which itself is going to be real now, k squared take away rho squared. So from now on, I shall write the square root of minus 1 in the usual way as I. Okay, so that's basically a kind of introduction to what I want to talk about. Here obviously we're looking at points of the circle which are imaginary. My question is, how do we understand all of the complex points of the circle? I mean, for a particular value rho, which is real, x squared and y, x and y, each of those could be a complex number, and then there's going to be several solutions to this kind of problem. Where are these solutions? How do we visualize them? If you think about it, we have two inputs to our equation, x and y. If each of those can be complex independently, they can each have a real and a complex part. So x is a two-dimensional quantity, and y is a two-dimensional quantity. So essentially we have the circle as a four-dimensional object now. with two real and two complex components. So how are we to visualize it? Is this kind of approach enough to understand everything about the circle? In fact, it is. And I finally managed to convince myself of that with a little bit of fairly simple algebra. So I like to go through that with you. Okay, so we're trying to get a handle on the complex structure of a circle by thinking about where the circle meets different lines. So we have this blue line here, which is a vertical line, a distance k to the right of the centre of the circle, which is the origin. Now, we can get this equation for where the circle and the line meet at the 2 points, and we can think of them geometrically in a way as a point which is square root of k squared minus rho squared above this place here, where the perpendicular to the line goes through the centre of the circle, where that meets this blue line. So we can visualise this distance above this particular point and the same distance below, and we can think of those as representations of these imaginary points. The x-axis is correct. These points are indeed k units to the right of the origin, but the y-axis is incorrect because it's real and it should be an imaginary thing. But apart from that, it is right that one of these points should be this quantity square root of k squared minus rho squared above here, and one should be the same amount below here. So essentially, by multiplying the y coordinates where the circle meets the line, we find by the square root of -1, we find these 2 points. And so then we can shift around, we can vary k, essentially sliding this line around, and we can plot all the places where the line meets the circle. When k is less than rho, the line will meet the circle at real points, and this procedure will give us the entire ordinary part of the circle. But when k is greater than rho, it will sweep out a rectangular hyperbola, and essentially that's representing the magnitude of the complex part of the meeting places of this line and this circle. So this kind of idea can also be thought of completely geometrically. I've talked about this in some of my videos on the geometry of imaginary and complex numbers. But today we're just going to think analytically. So we have this idea for one particular line, and then there is the notion that, of course, you can just rotate this around because the whole thing has symmetry. So instead of picking a line with this direction, you pick a line with this direction, and you slide it, and you get a very similar picture with a real circle, the same real circle, and then a rectangular hyperbola going away, showing you the magnitudes of the meeting points with the thing. So if you completely rotate this picture around, and you get all of the sort of copies of this for every angle, is that it then? Have you got a sort of sweeping understanding of the complex structure of the whole circle over the entire complex plane? I mean complex plane in the sense of complex field times complex field. Have you got an understanding of the entire structure of a circle from doing that? Well, the answer is yes, but I wasn't sure about that until today, when I found a way to get this same kind of idea of a picture without having to refer to the idea of lines intersecting with circles. You see, if our entire understanding is based on the notion of real lines, and we're talking about a fairly complicated, essentially four-dimensional object, you know, a little bit difficult to really have faith in that. So I'll show you this algebraic way to sort of connect with this, and it helps to interpret this kind of picture a bit better. Okay then, so this is the real meat of the argument, the kind of algebra of the thing. So we're starting off with the equation x squared plus y squared is rho squared. Rho is the radius of our circle. And we're going to suppose that rho squared is a real number. Now, what we're going to do next is to think of x and y as general complex numbers. So ax is the real part of x, bx is the imaginary part of x, so x is equal to ax plus bx times I, where I is the square root of minus 1. Similarly, y is ay plus b yi, where I is the square root of minus 1. So we can think of this in a bit of a novel way. We can think of xy as being equal to a real vector, ax plus ax ay with a comma, plus I times another real vector, bx by. So it's a real vector plus an imaginary vector, essentially, just like a complex number is a real scalar plus a scalar times I. Okay, anyway, that's just a way to think about it sort of visually, and we'll come back to the significance of that later. Algebraically, all that matters is that we take this equation here and substitute in these expressions for x and y, which include descriptions of their complex parts. So just substituting these into here and rearranging, we get this equation star, which is that 0 is equal to ax squared plus ay squared, take away bx squared, take away by squared, take away rho squared, that's the real part, and then the imaginary part, plus 2I times ax bx plus ay by. So that should equal 0. That's the condition for x and y to be on the circle when we're taking into account complex domains. So of course here the a's and the b's and the rho squared, they're all real numbers. The sort of complex issues are taken up by the presence of this term here. So what we can do, if we look at this equation again, we can see that in some sense x, y, those two things together sort of exist in a four-dimensional space. And we can think of that four-dimensional space as having these four components, ax, bx, ay and by. And we can break that up into two planes. This plane here, giving the real component of a point, ax and ay, and this part here giving the imaginary component of a point, bx and by. So these are essentially just two pairs of independent numbers. So we can think of them in terms of two planes. Okay, so we have a sort of real component plane upon which ax, ay are points, and we have a sort of imaginary component plane upon which bx and by are points. And what we want to do, in fact, is to understand. So if we have a picture of our circle on the plane, this is a normal real picture, and what we want to do is, if we pick a point, that will be given by coordinates ax, ay, that'll be a real point, and we want to then know what are the complex components going to be at that point. So essentially we want to understand how bx, by depends on ax, ay. So what we're going to do is, as I say, think of these as two different planes, but points in two different planes, And as such, we're going to use polar coordinates. So polar coordinates are a useful tool for when you want to talk about points in a space that have a kind of circular symmetry, such as the circle, right? So basically in polar coordinates you describe a point by a distance, in this case k, by its distance, in this case k, from the origin, and the angle theta of the vector that points from the origin to that point. Okay, so we're just going to, you can freely assume polar coordinates, you can just sort of introduce them, and you can always transform Cartesian coordinates into polar coordinates. So we're going to assume that this AX, AY plane is parameterized by polar coordinates, so that AX is equal to k times cosine theta, and AY is equal to k times sine theta. So this would be a sort of picture like this. This is the origin. This is the x-axis, this is the y-axis. This would be theta, and this distance here, that would be k. So that gives us this. Now we're going to think in just the same way about the BX, BY plane. So we're going to assume that that's also parameterized in terms of polar coordinates. Now, we're not yet going to assume there's any kind of interdependence between the A's and the B's. So we'll parameterize the BX, BY plane in an independent way, and we'll assume that a point on the BX, BY plane is parameterized so that BX equals R times cosine of phi, and BY equals R times sine of phi, where phi is a different angle potentially and R is a different number to k. So now what we're going to do is we're going to look at this equation star and try to figure out what R and phi are in terms of k and theta. So we're going to try and figure out how the B's depend on the A's. And to do this, what we can start by looking at is this thing here. So we have an equation here, all of the stuff over here is real, and this is the only imaginary part, and this equation is supposed to equal 0. So the things inside this bracket must equal 0. So we have this equation here. Now, if we make these substitutions into this equation, you'll see that the k's and the r's cancel, and the critical thing it comes down to is cosine theta cosine phi plus sine theta sine phi equals 0. And if you solve this for phi, you find that phi is equal to theta plus or minus pi over 2. So in other words, if we have a given direction theta, at which AX, AY is, then the sort of BX, BY vector is always going to be perpendicular. And we find, in fact, that there are two different possible solutions. It turns out that's the case, that there's these 2 points. We'll see the geometric significance of that later. So we solve for phi, we find it's basically, if we have a vector like this for the A vector, then the B vector is either going to be like this or like this. I'll do it like this or like this. In terms of direction, we'll talk about its magnitude R momentarily. So we have this expression that basically comes from considering this equation here. And if you think about it, cosine of theta plus pi over 2 is equal to minus sine of theta, and sine of theta plus pi over 2 is equal to cosine of theta. So when we make this substitution, it's essentially the same as saying that we have this expression here, that by is equal to plus or minus r times minus sine theta comma cosine theta. The plus or minus here is dependent on whether we add or subtract pi over 2 when we're going from theta to phi. So far so good. Next thing we're going to do is consider the real part of this equation and figure out what r is. Okay, so we're almost there. We've had this decision to express ax and ay in polar coordinates, and we've got this equation here by finding the relationship between the sort of real plane angle and imaginary plane angle, if you like. We found out that by is equal to r plus or minus r all times minus sine theta comma cosine theta. So essentially we have expressions for bx and by, except that we don't know what this constant r is yet. We don't really know what the magnitude is of this b vector. So we can go back to our equation star, recall that we found the relationship between the angles by considering the imaginary parts. Now let's turn our attention to the real parts. This must also equal 0. So if we do this substitution in here, so we simply substitute these values in for the a's and b's in this equation, then using this identity here that cosine squared plus sine squared is 1, this equation very quickly collapses down, in the real part of this equation collapses down into this one here, that k squared minus r squared minus rho squared equals 0. So then all we have to do is rewrite this in terms of r, and we find that r is equal to plus or minus the square root of k squared minus rho squared, a quantity which you might remember from the earlier pictures that we were talking about. So now we have r, we can put that up here, and essentially now we have an expression for the complex aspects of a point on the circle in terms of the real aspects of a point. So let's have a look at the geometric significance of that. Okay then, so now let's interpret what we've learned. The key thing that we found out from that algebra is that bx, by, this is the sort of imaginary part of our point, is going to be plus or minus the square root of k squared minus rho squared, and then there's that's all multiplied by these two possible components, the bx component, which will be minus sine theta, and the by component, which will be cosine theta. So this happens when the real part of our circle point, ax, ay, is just given by the standard polar coordinates of distance r from the origin, so it's k cosine theta sine theta. So what we can do is we can visualize this in a fairly straightforward manner, and I think it sheds a lot of light, at least to me, on what complex points are in this sense and what this kind of circle structure sort of looks like. So we have our circle of radius rho centered upon the origin, and then we have our x-axis. We pick an angle theta from the x-axis, and we pick a point, a real point that we're going to ask about, so ax, ay. And then we say, well, given that point, what's the imaginary components of the circle points there? And so we then just feed in the values into this formula, and we get an expression for this kind of complex vector. Now the meaning of bx, by geometrically is basically that this point is given by the vector sum of ax, ay plus I square root of minus 1 times bx, by. So essentially this point is described by a real vector and an imaginary vector. And so I think that's the nice way to represent what these sort of complex geometric points are. And basically, as a kind of wiggly blue arrow, in this picture at least, and that arrow originates from the kind of real part of the point, ax, ay, and it's the vector which specifies what bx, by is. So it's a vector bx, by emanating from the point ax, ay. So geometrically it's just the it's just this without the square root of minus 1 in it. We've just pretended the imaginary part's not there and added these two vectors together to get from here to here. But obviously if we do that, we lose information, crucial information, about how it has a real and an imaginary part, which is why it's best to think of it as a sort of vector, an arrow floating in the middle of the plane, starting from here. So it starts from the real component and it goes along here. And this has the very nice sort of bonus that it matches exactly with the sort of expression we were getting when we have a line like this saying, we ask where does it meet the circle. Remember in the first or second slide when I drew those hyperbola corresponding to that blue line shifting along? Well, if theta was 0, this picture would just be like this, and this arrow pointing up here, this will be exactly the arrow from that kind of cross-shaped black point up to where it met the dotted hyperbola. So this distance here, in fact irrespective of the angle, this distance up here will always be the square root of k squared minus rho squared. So essentially what we see here is that these two complex contact points, so it'll be one from this real point up here and one from this real point down here because of the plus and minus here, and these are complex conjugates to one another, and they sort of if we think of them really, they specify a real line, if we forget about the I for a second, and think of them in terms of this vector addition. And that line, if we take that line, then we get these points as the meeting point of a circle on the line. So there's a nice kind of symmetry here. I understand I'm not being particularly clear, but these are just things which I've worked out over the last few hours. So I'm still sort of processing what exactly they mean. Anyway, maybe a step closer to understanding what this complex structure of a circle really looks like. I'd say the main thing I like about this is that you don't make any assumptions before you start. You just load in these kind of, I have a circle, I'm looking for complex points on it. That's all you basically say, and you get this whole theory out. The theory works whenever rho squared is real. So we could have that rho is equal to I times some real constant. In other words, we can have circles with an imaginary radius. In that case, rho squared is negative. So then we won't have any real points. You see, all of these constants here are real constants, k and rho. Sorry, k squared and rho squared are real constants. So when rho is bigger than k, this term disappears. And in that case, the imaginary points on the circle disappear, because when you're within here, the points that you're going to get are real ones. Okay, so this does seem to basically give you the whole structure of the circle, apart from one thing. well, two things technically. The points of the circle at infinity. So let's just talk about those because they're very interesting. Okay, so it just seems like a good thing to do for completeness to then talk about the only two extra complex points on the circle to discuss. And so far I've been discussing a circle centered upon the origin. Now, of course, if we shift the circle around, that's not really going to make much difference. So now let's think of a circle which is centered upon the coordinates a, b. So this circle has the equation, and I'm now using r instead of rho for the radius. So it has the equation x minus a all squared plus y minus b all squared equals r squared. That's the equation of the circle. And now we're going to ask, where does this circle meet the points at infinity? So to answer this question, we're going to use homogeneous coordinates. And so I'm not going to talk about what homogeneous coordinates are in this lecture. I'll give you a link to another video where you can learn about that. But basically, homogeneous coordinates are a way that you can think about the kind of extended plane where you also have the points at infinity. So your normal points are specified by coordinates x and y when z is 0. Sorry, when z is 1. But when z is 0, you have points at infinity. Okay? So to get from the Cartesian expression for the circle to the homogeneous coordinate equation for the circle, we just take this and substitute in little x is big X over big Z, little y is big Y over big Z, and we get this equation of the circle in homogeneous coordinates. Using this, we can think about what's going on at infinity too. And then we can just reorganize this into this form here. And the points at infinity occur when z equals 0. So if you put z equals 0 into this formula, you get a very nice expression. Big X squared plus big Y squared is 0. And so we can solve that. Now in homogeneous coordinates, all that matters is the ratios of big X, big Y and big Z to one another. And we find that this equation is satisfied when the ratio of x to y is equal to plus or minus the square root of minus 1. And so essentially what this is saying is that every single circle meets the kind of line at infinity on a plane. Hard to wave my hands to illustrate what the line to infinity looks like, but assuming it exists, every circle meets it at 2 points, the same points, and those have imaginary parts plus or minus I. And so this is interesting because it doesn't depend upon the radius, and it doesn't depend upon the centre point AB. So it's true for every circle. They all pass through these two special complex points at infinity. And I've done a sort of geometric discussion of this idea in one of my videos on the geometry of imaginary numbers. I'll just put my hand there so that's shown. Okay, so thank you very much for your attention. Enjoy using this material if you do. There's certainly a lot of interesting things to study about the kind of complex extension of conics. Okay then, so what about more general situations? More generally, we can have a circle which is centered upon alpha and beta. And if such a circle has a radius of r, then it'll have this equation, this kind of equation. X minus alpha squared plus y minus beta squared equals r squared. And there's no reason with regard to our analysis why we can't allow alpha, beta and r squared to be complex numbers. The only thing is we probably shouldn't let r squared equal 0 for this particular argument. And in this case, what we can do is just rewrite this equation like this, and then we can see that if we simply substitute, so we'll do a sort of change of variables, so we'll let capital X equal X take away alpha divided by R, and capital Y equal Y minus beta divided by R. Then we get this new equation, capital X squared plus capital Y squared equals 1. So this is amenable to the same analysis as we've just gone through. So we can do the analysis introducing the sines and cosines and all the rest of it into this kind of system here. And then once we've figured out what's going on, we can just do this substitution back again. So this gives us a way to get a handle on the more kind of general types of circle. I presume they're all circles. I mean, I know at least one author that wouldn't regard these things as circles when R is a truly complex number with a non-zero real and imaginary parts. But I also know authors that would regard these things as generalised complex circles, so I shall refer to them as such. And so with these substitutions plus the previous method, we can think about, for example, how does the imaginary part of a circle point relate to the real part of a circle point as we change the sort of radius that the circle has. For example, if it has a radius equal to the square root of minus 1, the square root of I, in other words. In that kind of case, what's the difference, say, in the direction of the A vector and the B vector? We can study those kind of questions and basically try and get a handle on the more general structure of a circle in the kind of complex field. Now, this is all fairly new thinking to me, so although I suspect that it's well known in the community, in the wider community, but to me there's still quite a lot of questions I want to have a look at. So, I mean, for example, how is this interpreted? What's the kind of geometric interpretation of all of these generalizations of circles where alpha, beta and R are general complex numbers? Can we sort of get some handle on a space of all circles and what is it topologically equivalent to and so on? How do we think of circles in terms of polarities? So this is something I'm going to go into later. I'm also working on another series of videos talking about homogeneous coordinates and trying to give a better view of how projective geometry works in that sense. And it's perhaps more natural in a way to define a circle in terms of polarities of a kind of complex projective plane. So how does that work, and how can we get a kind of geometric interpretation of these circles which, you know, potentially could have an imaginary radius or whatever? Does such a generalized circle still pass through 3 points? If so, how can one deal with that analytically and geometrically? And can one use these kind of notions of a circle to build up things like a generalization of the Apollonian gaskets, for example, over the sort of complex field? What happens when you have two circles going through each other? How can one sort of generalize the standard theory of the different ways that two circles can meet, or that two circles can be configured on the plane. And what happens with circles of imaginary radius. So there's all these different questions, and some of them I think they deserve two different sort of treatments. They ought to be treated, in my opinion, via a kind of geometric approach, certainly with the polarities and the circle with imaginary radii. It's possible to study those things completely via the sort of van Stout geometry of imaginary components, but also it's possible to treat them synthetically as well. Analytically as well, using kind of algebraic approach. And there's so many other questions about the circle. I mean, pretty much all of the well-known circle theorems I think ought to be checked out in this kind of wider domain. And a lot of the constructions which we have in the real case ought to be extended. So there's still plenty of work to do.